6.1, velocity and net change. The thing we need to start with is discussing displacement versus distance. Displacement is how far from a starting point you get. It is the change of position over time. It is basically magnitude and direction. Displacement always has a direction. And distance is actually how far you've traveled. So there's several different ways we can actually draw pictures to think about it. If you were going to start here at some place and you traveled directly west some distance and then you actually traveled north some distance, this would be distance, how far you actually traveled, but this would be displacement, how far you are from home. And that's totally not legible. But there's a difference between distance and displacement. So remember, displacement can have direction and magnitude. Distance is basically a linear distance. So here's another way of thinking of it. If you're a boat that you went in on a lake and you decided to go in a completely circular path and you ended up coming back to where you originally left, you have a zero displacement, but you went the complete circle of a distance. So you could have zero displacement and displacement and distance are not equal. You can have an example of where they would be equal, as if maybe you're in this boat, you left the dock and you drove your boat in exactly 200 miles away. You have a distance of 200 miles and you have a displacement of 200 miles east. You would say east because that's the direction you went. So you could have displacement and distance being equal or not equal. And also now we want to try to interpret this in terms of calculus. So if that's the case, with displacement, I may be given a function like this, and I want to try to see how I have a total area, but it's not total area. I'm actually going to look at net area. So I'm going to be looking at net area for displacement. And for distance, then, I need to figure out exactly, so maybe this function looks more like this, and I'll have a total area. So then how do I go ahead and use my integration methods for finding displacement and distance? And that's where our little chart comes in. We have the position of an object at time t is the location of the object relative to the origin. The velocity of an object is v of t, or the derivative of position. Displacement of the object from some time a to time b, as long as b is greater time, then we can see that it is the position s of b minus s of a is equal to the integral of the velocity. So this is displacement. And then we have the distance traveled is going to be the total area or absolute value of this. And that is the key difference here. This is just the area. This is net area. And taking the absolute value will give us a total area. And where the absolute value of the velocity is remembering speed. Velocity gives us magnitude and direction, and speed is just a magnitude, no direction. All right, so we are going to go, let's go ahead and go back and do a couple problems. Let's start with number 7. I'm given that the velocity is 6 minus 2t, and we're going to be going from 0 to 6. And we can draw a graph of this, roughly. It would be looking like this. And we were going from 0 to 6. We would graph like this. And we want to know positive and negative direction. So we're going positive when we're from 0 seconds to 3 seconds. And we will be going, oops, negative from 3 to 6. Notice on our intervals here that we are not including 3. 3 is that special case. It's not really belonging into our positive or negative, and that might be at that moment of rest that we went one positive direction, and at moment of rest we came back the other way. Remember, if you are in physics, you might have done velocity as far as going this way, and we could say 3, and then we went this way for 6. Okay, so that was another way you can denote this. And then for part B, we want to go ahead and find displacement. So we're going to go ahead and take this integral and we're going to calculate. And if you notice from our previous graph, it should be 0. We end up back where we started. So part C then is talking about distance. And then for that, we're going to take the absolute value, and we get that it should be 18. I believe they did give us meters in the problem, but I do not have that in front of me. So if we want to go ahead and let's try another one that has some trig with it. Let's do number 13, saying it's sine of t on this interval from 0 to 2 pi, and a position, initial position here at 1. So we want to go ahead, in part A, we're going to do a quick sketch. Should look like this. Oops, not really quite scale. But we know what the sine wave should be. This should be at pi, and this should be at 2 pi. So then I can go ahead and tell you where we're going in a positive and negative. And we have that we're positive from 0 to pi, and from pi to 2 pi, we're negative. We're below, above and below. And notice that in this case also, because of the function sine t, pi is not included, 0 is not included, and 2 pi is not included in our interval of positive and negative. So for part B, we want to go ahead and we said, okay, we're going to take sine of t. We want to find the velocity, take the velocity function and find the position function. So we're going to take the antiderivative and get negative cosine t plus c, and then they gave us that initial value there. So we're going to go ahead and say c really was 2 when I plug this all in. Cosine of 0 plus c, this is negative 1. C is then 2, and then when I go ahead and say the position function is negative cosine of t plus 2. And then part C does ask you to graph the position function, which is easy to do. All right, I want to start with 21. We're given this velocity function in this form on this interval and this initial condition. And what they want us to do on this one is we're going to go ahead and graph velocity. And if we graph really quick sketch, it's not straight, it's slightly curved. It's really hard to sketch that one. And then if they want to say, okay, what is the distance after 2 hours? So here's the thing. We're given velocity, and we kind of, in order to find the distance after 2 hours, I have to find position. So I'm going to go ahead and find the position function, say s of t, and I get 4. What I did was I went ahead and expanded this in this form and took the antiderivative of that. So I really then, when I simplify this one, I'm going to get 480t minus 10t cubed plus c. But in this one, because of my initial condition, and this is something the book says in this section, instead of writing this, I can do s of 0 plus the integral of the velocity. And I should then go ahead and be able to save myself the step of finding initial condition and a C. And since my S of 0 is equal to 0, my C is 0. So I can actually almost save myself that step, and I have that plus 0 at the end here. So now this is my position function, and they wanted to know when it was 2 hours. So I'm going to go ahead and plug in 2 into this equation, and I should get 880 miles for where I am from when we started. Part C then says when the velocity is 400 miles per hour, uh, where are we? We want to know position. So what do I have to do here? And this is the case then where I'm going to go ahead and take my initial velocity function, and I'm going to set it up equal to the 400 miles per hour. I'm going to find t, and I think I missed my 30 up here. Hold on. It was 480 minus 30t squared. And then I'm going to set it equal to 400. I'm going to find the time when velocity is equal to 400, and then I'm going to plug that time into my position function so that I know where were we when we had a velocity of 400 miles per hour. So if this is the case, I get t equals the square root of 8/3, and I did not rationalize this one because I'm plugging it into, oops, 8/3. And I'm plugging into my position function. And I get roughly that it's 740.29 miles from our initial starting position. That's our S position function evaluating at this time when velocity was 400 meters. We should be able to go ahead, and last one, number 25 would be one I just said earlier. Same thing with position. If we could break that down into and then if that's the case, then it also applies with also our acceleration. So we can use that at one. So number 25 would also follow that. And we could do, I'm sorry, it's velocity given acceleration. There we go. So this is also another case. We can call this future position, future value. It just makes it a little bit easier when we go ahead and give in some initial values. So this is the end of this section.